Reinforcement learning in VPPs uses several mathematical principles. Optimization theory. VPPs aim to optimize the use of various energy resources, for example, solar, wind, and battery storage, to meet electricity demand efficiently. Optimization techniques such as linear programming, nonlinear optimization, and mixed programming are crucial for formulating and solving the optimization problems encountered in VPPs. Stochastic processes. VPPs often operate in uncertain environments due to the variability of renewable energy sources, for example, solar irradiance, wind speed. Understanding stochastic processes, including time series analysis, probabilistic forecasting, and Monte Carlo simulation, is essential for modeling and predicting the behavior of these energy resources. Power systems analysis. Knowledge of power systems engineering principles is essential for understanding the interactions between different components in VPPs, such as generators, transformers, and transmission lines. Concepts such as power flow analysis, voltage stability, and frequency control are relevant for designing and operating VPPs efficiently. Markov decision processes, MDPs. MDPs provide a mathematical framework for modeling the sequential decision-making process in VPPs. States represent the current system state, for example, energy demand and energy prices. Actions represent the control decisions, for example, dispatching resources, and rewards represent the system objectives, for example, profit and reliability. Algorithms can be applied to learn optimal control policies for VPP operation based on MDP formulations. Improvements for VPPs from reinforcement learning and examples. Applying these techniques to a VPP can unlock significant improvements across different functions. 1. Dynamic optimization and real-time decision-making. VPPs operate in a constantly changing environment with fluctuating energy prices, weather patterns, and consumer demand. Traditional rule-based systems struggle to adapt effectively. Reinforcement learning excels in such scenarios. The VPP agent can continuously learn from real-time data and interactions on energy generation, grid conditions, and market prices. Based on rewards, for example, maximizing profit or minimizing grid imbalance and penalties, the agent can dynamically adjust VPP operations. Optimizing energy generation. The agent can, for example, learn to strategically charge and discharge batteries to store excess renewable energy for peak demand periods, maximizing profit by selling electricity when prices are high. Participating in demand response programs. The agent can learn to adjust energy consumption of participating homes and businesses based on real-time grid pricing signals, reducing peak demand charges, and contributing to grid stability. The agent can assist in strategic bidding and market participation and learn optimal bidding strategies to maximize revenue while adhering to regulations. 2. Improved forecasting and proactive management. Forecasting energy generation from renewable sources is crucial for VPPs. Traditional methods rely on historical data and weather patterns, which can be inaccurate. Reinforcement learning can integrate historical data with real-time weather updates and continuously learn from past forecasting errors. This allows for more accurate predictions, enabling the VPP to proactively manage resources and make better decisions. 3. Advanced asset management and maintenance scheduling. VPPs rely on a mix of DERs, and maintaining these assets is vital for optimal performance. Reinforcement learning can analyze sensor data from DERs to predict potential equipment failure. Based on this prediction, the agent can schedule preventive maintenance, minimizing downtime, and maximizing VPP efficiency. 4. Self-healing and grid resilience. Disruption. Power grids are susceptible to disruptions from natural disasters or equipment failures. VPPs with reinforcement learning can play a crucial role in enhancing grid resilience. The agent can learn to identify and respond to grid disturbances in real time. It can automatically adjust VPP operations to isolate faults, maintain grid stability, and facilitate faster recovery. Uncertainty handling. DERs are uncertain. For example, solar output varies with clouds. Reinforcement learning models adapt to this uncertainty. They learn to adjust schedules dynamically, improving reliability. Safe exploration, Reinforcement learning balances exploration, meaning trying new actions, and exploitation, meaning choosing known good actions. In VPPs, safe exploration ensures reliable operation without risking critical failures. A good example for reinforcement learning in a VPP is the deep deterministic policy gradient, called DDPG algorithm. The DDPG is a popular algorithm for learning continuous action policies. It has been used for strategic bidding of VPPs in day-ahead electricity markets. The algorithm enables VPPs to learn competitive bidding strategies without requiring an accurate market model. Additionally, enhancements like a projection-based safety shield and a penalty for shield activation are introduced to account for the complex internal physical constraints of VPPs. Centralized coordination and control of DERs is problematic, for example because of failure and system disruption, security, and privacy. Research also proposes novel base distributed optimization methods for VPP coordination. These methods expedite solution search, reduce convergence times, and outperform traditional approaches. Challenges for AI in a VPP. There are also significant challenges for AI in VPPs, and a few highlights are as follows. Complexity and training. Implementing and fine-tuning AI algorithms for VPPs requires expertise and substantial resources. The complex and dynamic nature of the power grid can make it challenging for the AI agent to learn effectively. Data security and privacy. VPPs handle sensitive energy data. Ensuring data security and user privacy while collecting data for AI training is crucial. Reinforcement learning is data hungry. It requires even more data than supervised learning, as well as many interactions to learn effectively. Getting enough training data is hard. Most of the data for AI stems from IoT devices. This raises additional security concerns. Explainability of decisions. Understanding the rationale behind the AI agent's decisions can be very difficult. This is a concern for ensuring VPP operations comply with safety and grid regulations. System-level and physical constraints are not easy to integrate, and this can create additional security risks. Conclusion. Despite these challenges, reinforcement learning holds immense potential for optimizing the operations and performance of virtual power plants. As innovation and technology matures, reinforcement learning can revolutionize VPPs, leading to a more sustainable, efficient, profitable, and resilient energy system.